Okay, here we are again. This is video lecture 16.1, part 2, and I want to talk about section 2 in chapter 16, which is going to focus on wave speed on a stretched string. And really, we probably ought to say velocity on a stretched string. And in fact, one of the things that can be a little bit confusing is that there are two different velocities for a wave, a sinusoidal wave on a stretched string that we have to keep track of. Okay, so let me try to explain what those two velocities are so that we can keep them distinct in our mind. Again, I'm imagining the scenario that I talked about in the previous video, a taut string, a string under tension with a certain mass per unit length mu that would normally just rest on the x-axis. And then way over at one end, we are moving that end up and down, perpendicular to the x-axis, in the y direction, with simple harmonic motion. And we let that just keep going. And that will produce a sinusoidal wave that will travel in the plus x direction in our case. What's the velocity at which that wave, that disturbance, propagates? Well, velocity has a magnitude and a direction. We know the direction is plus x because of the way we made the wave. What determines how fast, though? Just the speed of that wave, okay? All right. So first we have to acknowledge that in a uniform string under tension, the speed of the wave, and we use the symbol v for that, is constant and is the same everywhere along the wave. The full-blown vector v arrow points in the direction the wave travels. So if we look down below at my little drawing, it's a simple representation of a sinusoidal traveling wave taken at a snapshot t, and I just showed one wavelength of the wave. It repeats on either side, okay? And this is a snapshot at a time t, with picture of the actual string at time t. And now I'm showing you one wavelength. And I've shown with an arrow to the right a representation of the wave velocity, because the disturbance is traveling in the plus x direction to the right at velocity v. But remember something I emphasized in the previous video. If you look at any little piece of the string, any small segment of the string, it moves perpendicular to the v, up and down. Because remember, this is a transverse wave. That's what transverse waves do. And the speed of each little segment of the string is not constant because each little segment moves with simple harmonic motion. Let me try to emphasize that with this point right here. There's my red dot on a piece of the string. If I were to follow that red dot with time, it would move up and down along the y direction with simple harmonic motion. And therefore, every little piece of string is moving up and down with simple harmonic motion. So every little piece of string is a simple harmonic oscillator. So my wave is an infinite number of simple harmonic oscillators, and each one is connected to one neighbor on its left and one neighbor on its right. Now you see why we had to do oscillations in chapter 15 before waves. So look at this little piece of the rope with the red dot at this snapshot t. I've got a couple of things labeled here. First of all, this downward arrow labeled y is just the y displacement of that piece of string. And that y displacement would be given by this wave function we talked about in the previous lecture. Y max times the sine of kx minus omega t plus phi. So I would plug in this x value right here and this t value right here into this formula right here, and that would tell me the y right here. But that little piece of string, at the moment we took the snapshot, was moving. So it has a velocity. Now this velocity it happens to be straight down. That's this red arrow right here. It's not the same thing as the velocity of the wave. The velocity of the wave is to the right, denoted by the symbol V arrow. The velocity of this one little segment of rope happens to be straight down in the negative y direction in this case. So we're going to call this the transverse velocity of a string segment. Transverse because it's in y, not along x. And we have a completely different symbol. Not V. It has nothing to do with V. It's U arrow. That's the symbol we're going to use for transverse velocity of a string segment. That's what I mean when I said there are two velocities to keep track of. Two kinds of velocity. There's the velocity of the wave, which in our case is to the right, and as the clock ticks away, that's not changing. And then there's the velocity that you have if you focus in on any particular little piece of string in its up and down motion. And that's simple harmonic motion. And that velocity is called the transverse velocity of the string segment, denoted by the symbol U. And the U is not constant, because a simple harmonic oscillator's velocity is not constant. Now you might be wondering, how do I know that in this snapshot, for that little piece of rope right there, that when we took the snapshot, it was traveling down? How did you know it wasn't traveling up? But I do know it's traveling down. And I know from the picture. Okay? Two things. One, I know the wave is traveling to the right. So to know what's about to happen to my little piece of string, look to that piece of string's immediate left on the rope, on the waveform, because that's what's coming down the pike. And look what's immediately to the left of my little piece of rope. It's a piece of rope that's farther down, lower. That's what's coming down the pike for my little piece of string. And therefore my piece of string has to be moving down, because the next piece of the waveform that's coming is lower down. So the picture tells you that the transverse velocity of this little string segment at this moment was downward. That's how I knew to draw the arrow labeled U downward. Okay, so there's V and U, two different velocities. The wave velocity V, which is constant, and the transverse velocity of any particular piece of string, which is always changing. How do you calculate that U? Let's say you want to know what it is. How do you do it? How do you find it? All right, I'm going to tell you that next. Right there. Here's going to be the function for calculating U. U has two independent variables, x and t, you got to plug in. You got to tell me where are you on the x-axis and what is t. And then I want to be able to tell you the U, the transverse velocity at that point. Well, it is a velocity, but it's a rate of change of the y coordinate, not of x. It's up and down, rate of change of y. So I want the rate of change of y. What y? The y function of the wave right up here. That rate of change. Okay? But here's the subtlety. That function y, that wave function y, has two independent variables, x and t. Y depends on two variables, x and t. But I only want the rate of change with respect to the t. That's what velocity is about, rate of change with time. So how do I do that derivative for that function y when it depends on two variables, but I only want the derivative with respect to one, the t? Simple. Treat the other variable x as a constant, and then just take the derivative with respect to t. That's called, in calculus, a partial derivative. Okay? A partial derivative. And the notation for a partial derivative, look very carefully, is not d by dt. That's the notation for an ordinary derivative. For a partial derivative, you use a curly d. Curly d by dt. And that tells your reader that you're taking the partial derivative of a function that depends on t and other variables, but all the other variables are to be assumed to be constant. So here's the notation I'm talking about. the partial derivative of the y function with respect to the t variable. And the y function is right up here. So we take the partial derivative of that function with respect to t. That means treat everything except t as a constant. Y max, k, x, omega, phi, all constants. You do need the chain rule because I've got y max sine blob, and I need to differentiate that with respect to t. Well, the derivative of sine blob is cosine blob times the derivative of the blob. Okay, so I've got a y max out front. There's cosine blob. Now the derivative of the blob means differentiate this with respect to t, treating k and x and phi as constant. And when you differentiate that with respect to t, you have just a negative omega. And notice that's out front there. Negative omega y max cosine blob. And so you can use that function to calculate the transverse velocity of a piece of string. Okay, I'm going to close this video with just a couple more points and then a class engagement exercise for you. We've had quite a few formulas here, but let's not lose track of physics and the physical situation. And so I want to talk about some physics for a moment with regard to our traveling waves. First question: what physically determines the frequency f, and therefore the angular frequency omega, since omega equals 2 pi f, what physically determines the frequency f of a wave? What determines how many up and down periods a piece of rope completes per second? That's an important question I want to address. And the answer is the frequency of the wave's source. Okay? So my question was, what physically determines the frequency f of a wave? Answer: the frequency f of the wave's source. So I've got some machine at one end of the string going up and down with simple harmonic motion. Whatever I set the frequency of that up and down motion to be, that's going to be the frequency of the sinusoidal wave. Okay? That's what physically determines what the frequency of a wave is. The frequency of the wave's source. Next, what physically determines the speed v of a wave? How rapidly the disturbance propagates? What physically determines that? Answer: properties of the medium on which the wave is traveling. Okay? What physically determines the speed v of a wave? Properties of the medium on which the wave is traveling, for a mechanical wave. We've been focusing on a wave on a taut string, transverse wave on a taut string. You can derive the formula for the speed v of such a wave. If you want to see that, it's in chapter 16, section 2 of your book. Although I'll warn you, it's a pretty complicated derivation. I'm just going to tell you the result because we're just going to use it, and at least show you that the result has the right units. But I want to emphasize that this formula for the speed of a wave on a string depends on properties of the string. And the formula is right here. The speed v of a wave on a string is the square root of the tension in the string, I label that F sub t, over the linear mass density, or mass per unit length, in kilogram per meter, mu. Two properties: tension of the string and its linear mass density, or mass per unit length. Those are both properties of the string, the medium. If I make the string more taut, put it under more tension, then a propagation will travel faster. If I replace one string with one that has a larger linear mass density, that string is going to be more sluggish, and the speed v of a wave, a disturbance on that string, is going to be less. So it's a pretty simple formula, and it depends on the tension and the mass per unit length. Let's at least check the units. Let's show that the square root of tension over mass per unit length in SI has units of meters per second. Okay, so inside the square root, remember, means 1/2 power. I have a tension in the numerator. That's a unit of Newton. It's a force. And in the denominator, I have mass per unit length, which is kilogram over meter. Now let's remember what the unit of Newton is from F equals ma. A Newton is a kilogram from the m, and a meter per second squared from the a. So that's what a Newton is. So now I have that expression. But then I have a kilogram upstairs and downstairs. So the kilograms cancel. I have a meter in the denominator of a denominator, which actually means it's in the numerator. So what this really is meters squared over seconds squared to the 1/2. And when I take the square root of a meter squared, it's a meter. And the square root of a second squared, it's a second. So sure enough, that quantity, square root of tension over mass per unit length, has units of meters per second. And that's how we can find the speed of a traveling wave on a string. Square root of tension over mass per unit length. That's the v, not the u. To get the u, we have to use that formula right up above that you see. Okay, so the last thing I'm going to say is I just want to share with you that I have a little class engagement exercise that you are to answer on Blackboard. Just a couple of questions about some transverse traveling waves. Okay, and we are given the equations of 3 waves, 1, 2, and 3, the wave functions, y of x and t, where the x is in meter and the t is in seconds. You can see those wave functions on the right. And then just some questions based on those wave functions. A, rank the waves according to their wave speed v, largest to smallest. So there must be a way, with the information inside these wave functions, to figure out the v of the wave. That was in the first video lecture. So basically, find the v for each wave, and then you can rank them, largest to smallest. B, rank the waves according to the maximum transverse speed of the string elements, largest to smallest. The u maximum. There must be a way for each wave function to actually get the numerical value of u maximum. Go ahead and do it for each wave, and then rank them from largest to smallest. C, rank the waves according to the wavelength lambda, largest to smallest. Again, from the wave functions and those numbers you see, you can figure out lambda, the wavelength. So figure it out for each wave and then rank them, largest to smallest. And finally, rank the waves according to their angular frequency omega, largest to smallest. Again, from the numbers you see here, you can get a number for omega. Do that for each wave and then rank them. Okay, so just enter those rankings for those questions on Blackboard. Okay, that's going to be all for this video. There'll be one more for Thursday. That'll be our class video, in which I'll do more example type problems. But that's all for this video.